Hello everyone, this is Stuart Wright. I first off want to thank the organizers for their efforts to gather us virtually. I know they'd much rather have us all there in Osaka, but hopefully we can gather in the near future. The organizers of this symposium have asked us to talk about what we see as the future of EBSD, and we're grateful for the opportunity. I want to acknowledge my co-authors Matt Nowell and Will Lenthy, who has recently joined us from Carnegie Mellon University. I also want to thank all of the contributors. We've reached out and asked for slides and figures, and many of you have contributed generously, and we're grateful for that. I've tried to put a lot of detail and a lot of references, although certainly not comprehensive, on the slides, much more than I will ever cover, in the hopes it will help you if you're interested in any of the topics that we present. My first ICATOM was in Santa Fe in 1987, and at that ICATOM, David Dingley gave a talk about EBSD. In attendance for that talk was Professor Brent Adams, who was my advisor at the time. I was just a young undergrad, and we were working on orientation coherence functions. And the idea there was to create a statistical description of the microstructure, particularly of the crystallographic orientations. And with that, we needed to measure point-specific orientations as rapidly as possible, and what we had done was already difficult with a lot of digitizing, which was my assignment. And so he recognized that EBSD could be a real solution to the challenges that he was facing. Brent took his research group to Yale University shortly after the EBSD introduction, and we started working on automating the EBSD. We were successful and were able to index points at a rate of 4.3 seconds per point on a $100,000 mini supercomputer. Today's systems are nearly 20,000 times faster and on a much cheaper computer, so we've made great strides. I originally thought that we would have plateaued by now in terms of the development of EBSD, but that certainly is not the case. We continue to see more and more papers being published using EBSD, and I would say in the past decade we've seen an increase in the number of papers on technological development. Originally, the vendors used to drive EBSD technology due to competition and the demands of their customers, TSL and HKL, then EDAX and Oxford and Brooker. But now the number of customers we each have is quite large and much more varied than it was originally, and the expectations are higher, and it takes more complexity to get new steps in technological development. And so we now see that the research community is really the one pushing the technology envelope, and we are simply trying to keep up through incorporating those ideas. So as where I see some of these ideas going are in modern algorithms, correlative microscopy, dynamic pattern simulation, advanced analysis of the EBSD patterns, the detectors, 3D, TKD, sample prep, and some of the challenges that we still face. And I'll talk about all those. My view of the future is biased to what I see from our most communicative customers, from the conferences I attend, the papers I read and review, and I certainly don't see everything. So some of the look forward I'm going to give has been around for a while, and the ideas have percolated, but they've really taken off with new technology and frankly new voices and eyes on the problems. And so I think there's a lot of exciting directions for the future for EBSD. So let's first talk about some of the more modern computer algorithms. I'll start with some machine learning example within the realm of crystal symmetry, and then move on to feature analysis, including multivariate statistical analysis, and how that leads then into smart scanning. And in terms of smart scanning ideas, it's not all about algorithms. There's also hardware challenges we'll have to overcome to implement some of those smart scanning ideas. Early on, crystallography was very much the focus of EBSD work, particularly of David Dingley's work. Later on, Joe Michael jumped in and had a lot of good ideas as well in the area of phase identification. Since then, indexing and orientation, kind of microtexture work has taken over, and crystallography has lagged behind. I think there's a real opportunity for EBSD to play a greater role in things like crystal symmetry and phase identification. Machine learning has been applied to the problem of resolving crystal symmetry elements. In this case, they're separating different Bravais lattices. This is a group at UC San Diego. They've also applied this to differentiating different point groups and working as well on extending it to space groups. And so far, the results look quite promising. Another idea is to couple EBSD with feature analysis, existing feature analysis methodologies, which are well advanced over the years, but haven't really been married together as well as they should. we have the idea of, in this example, of just an EBSD IQ map. And using some image segmentation tools, we're able to separate the two different phases away from each other that EBSD has a hard time differentiating, but we're able to tell from the morphology. And so then we use that image segmentation to classify the individual orientation measurements in our scan grid. And that's just one application. You can imagine certainly many others that could benefit from coupling these two technologies together. One example of that is EM-NPM. The idea is that instead of using a simple threshold to separate a binomial distribution that you see there on the right, the idea is that we know that we'll misclassify many of the points in the trough with a simple threshold. And so if we apply more sophisticated means, then we can start to differentiate these areas using this type of analysis. And that then leads into the idea of smart scanning. Can we use such analyses to find grains, to find phases, to help us and improve our data acquisition strategies? And along with that is the idea of sparse data representation, and it also, the key is non-gridded data collection. So if we have an image of some kind, whether it be from an FSD, a secondary detector, from the EBSD detector itself, as I'm showing here, we can use that data to find the grains. Once we found the grains, then we can collect one pattern per grain instead of collecting patterns on the grid. And this obviously could give us a tremendous speed up and would be very appropriate for materials with constant orientations within the grains. It might be a little more difficult for deformed materials. But there are other strategies besides that that could be helpful in deformed materials or other materials. You can imagine starting out with a very coarse scan grid and fairly coarse patterns in terms of the lower pixel resolution in the patterns. And then there might be features of interest. One example is grain boundaries that was actually presented at the Montreal Icotome in 1999. But you can imagine other features. So example, in this case, there's a lot of points with very different orientation in the region I've highlighted there. It would be fairly straightforward then to go back in and scan that area at a finer step size and maybe with higher pixel resolution. Maybe we want to do HRDIC in there, so we want to collect much better patterns. So you can imagine these kind of strategies based on that are really feature driven in terms of smart scanning. You can also imagine then instead of even if you do collect data on a grid, to represent that data as individual entities. So instead of a grain being a collection of points, a grain is a grain, and maybe associated with that grain is an orientation, the size, the grain boundaries surrounding it in terms of both misorientation and maybe even curvature. So this points the way towards ideas that are used in the synthetic microstructures, for example, to increase our analysis capabilities and really to make things quicker from the way we do them today, to go to a more sparse data representation. Another example is the use of multivariate statistics, component analysis or phase cluster analysis, if you will. And there we get one pattern per component, or in this case, in this example, it's per grain, but there may be other ways to look at that. And this kind of analyses could really help us get better patterns through averaging within specific features, but there are certainly other applications. One area that has seen widespread growth is coupling EBSD with other analytical techniques to get a better understanding of various material science problems. And I'm going to show an example for strain analysis, but you can imagine many other applications for correlative microscopy of EBSD with other techniques. I mentioned earlier in our glance backwards that Brent Adams was working on this orientation coherence function as a statistical description of microstructure. Now this was focused on orientation, but it certainly could be expanded to any descriptor of the material state, whether that be chemical composition, dislocation density, or whatever it might be. In fact, the idea of statistical description of microstructure really is an area that I think that could be expanded. That's not just an EBSD thing, but an area that is part of material science that I think will grow as well. Anyway, this idea of material state at a point certainly points the way to correlative microscopy. But if we apply that kind of idea, then we can use like EDS to find the composition at a point and link it with orientation. And this is our first effort at that back in 1997. But things techniques have gone much beyond that. Here's an example of AFM correlated with EBSD, and this allows us then to correlate the crystallographic orientation with the surface topology. Another example is the use of EBIC and cathodoluminescence with EBSD, in this case to explore the impact of grain boundaries on the photovoltaic behavior in this material. Similarly, we can correlate micro-Raman results with EBSD and to understand other parts of our microstructure. I mentioned TKD. This is just an example of using TKD to look at the three-dimensional nature of a grain boundary crystallographically using EBSD, and then link that with the atomic species that we were able to get from the Atom Probe data. There's other examples of using EBSD to find features of interest and then fib those features out and put those in the Atom Probe for further inspection. So let's look at deformed materials. We know EBSD is very good at helping us understand deformation processes in polycrystalline materials. But there's complementary techniques that can provide us a better picture, a more complete picture of the deformation process. And just as some examples, here's bright field TEM coupled with HREBSD to measure the geometrically necessary dislocation density. And so you can compare these images and get an idea, of what's going on in the material in more detail than you can from either one alone. Similarly with ECCI, which enables us to identify individual dislocations in the microstructure, and we can compare that to what we get with HRDIC, giving us confidence and confirmation of what we're seeing, as well as increased understanding. Another approach is to use high-res digital image correlation, HRDIC, and in there you speckle your surface with some kind of coating that allows that you can track as you deform the material, and then you couple that with EBSD. Here's a very nice example showing DIC work on a strained nickel superalloy, and we compare that then with individual G-rod maps, which are show the deviation at each pixel in orientation from the average orientation within the grain. And you can see there for several different slip conditions and compare the two. And I think this picture is interesting because it not only tells us what we are measuring with EBSD, but it also tells us what we're not measuring. And that distinction is actually important. And this slide from Professor Fonseca, University of Manchester, I find quite helpful. Where you see on the left is the HRDIC and what we see there versus what we see with EBSD. And then both of those contribute to the full picture of what's happening within our material or within the specific grain that we're looking at. And so it's very helpful. Another complementary technique would be high-energy X-ray diffraction microscopy, say at one of the beam lines. In this example, we see the evolution of a grain and its orientation with increasing strain. And this has the advantage of being done in the bulk, whereas EBSD suffers with free surface effects when doing in situ work. So what are some of the challenges with correlative microscopy? One, image registration. We, for EBSD, are at a high tilt, and we must compare typically against non-tilde condition. We have differences in resolution, which can give us different information because of the resolution, but linking them something we have to be concerned about. We have instrumentation issues, drift, geometry, stability, those kind of things that also are challenges. As an aside, indexing has been used with other techniques. The things we've learned from EBSD-based indexing, we've applied to other types of patterns from other microscopic imaging modalities. Another big area that I see a great future in, and we're already seeing, is dynamic pattern simulation. And let me show you some of the ideas that are there, that are already there, and that are increasing in both application, but also in advancing the techniques. So we started out with kinematic simulation to understand our EBSD patterns, to understand which reflectors we expect to find, and that helped us in our Hough indexing. But a kinematic pattern, simulated pattern, doesn't look anything like an experimental pattern. It gives us just enough information to get started with indexing. But with dynamic simulation that has been pioneered by the two groups of Imo Winkelmann and Mark de Graaf, have really come a long ways in both the fidelity between the individual patterns, the simulated patterns and experimental patterns, but also in speed and usability. So with those, we are able to simulate patterns that look quite a bit like experimental patterns, as you can see in this example. And that's great, but what can we do with that? Well, I think the biggest area that you've probably seen is dictionary indexing. Instead of indexing by band detection, we take an experimental pattern, compare it against a set of simulated patterns that fill up basically a dictionary. Those patterns are calculated on some grid through orientation space and cover all of orientation space. And we just use a pretty simple comparison for each pattern in the dictionary against the experimental pattern, and we find the best match, and then we've indexed the pattern. So as you can see here, it works really well, especially as the patterns get poor. You can see in this case we've increased the gain to increase the noise in the patterns to artificially degrade the pattern quality. And you can see in that last column there on the right that we have really couldn't reconstruct the microstructure at all with regular Hough-based indexing, but did quite well with the dictionary indexing. Because of this discrete nature of dictionary indexing, the step size used in sampling orientation space will very much affect our ability to capture smooth features in grains in the orientations, like an orientation gradient within a deformed grain, as you see here. As we decrease the step size, we greatly increase the number of patterns in the dictionaries, and as we decrease in crystal symmetry, we also increase the number of patterns in the dictionaries, and this puts a load on our computational resources and capabilities. So we do some on-the-fly simulation of the patterns as we get close, and we can do orientation refinement. And that allows then us to capture those gradients smoothly that we see particularly in deformed grains. To speed things up, there's been recent advances using spherical harmonics. So this is basically a cross correlation of the master pattern against a back projected experimental pattern. It's analogous to doing the indexing in Fourier space on a sphere. And with that then we can index much more rapidly. It depends upon some things like bandwidth, but I won't go into the details there. Just to say that we may need more bandwidth depending upon the quality of the patterns and the quality of the indexing we're seeking. So as an example, in a shot peened aluminum alloy with 3.4 million patterns, dictionary indexing operating on 24 cores and a GPU took 82.5 hours plus another 30 hours to do the orientation refinement. The beginning step was a 1.4 degree step size dictionary. The spherical indexing was CPU only at this point, 24 cores. It does include orientation refinement already, and it took similar quality to dictionary indexing. It took 50.7 hours. So you can see we got quite a bit of speed up. I anticipate dictionary indexing, including spherical indexing, to help us more with pseudosymmetry. We've seen some of that already, but I think we're going to see greater advances there, that we can resolve pseudosymmetry problems or at least predict them, and then that should help us resolve them as well. Same with phase differentiation. In this case, we would compare one master pattern versus another for two different phases. And that cross correlation of those two master patterns then would give us a clue as to when we can differentiate phases and when we might have difficulties. This is just an example from feldspars. We've used simulated patterns to help go backwards to help us improve Hough indexing. When we have a new material, we don't know which bands to expect. We can use the simulated patterns to help us find out which reflectors we need to do our indexing. The group at CMU, Mark's group, has really come a long ways in terms of starting to look at lattice defects. This is just to show an example of the effect of 100 edge dislocations within an interaction volume on the quality of the pattern. And you can see those results there. The smearing of the pattern due to the dislocations within the crystal lattice, within the interaction volume. So we can use some of that information, the dynamic pattern simulation, and incorporate it then into some of our advanced pattern analysis. When I think of advanced pattern analysis. I think the best example is HREBSD, the pioneering work done by Wilkinson. He initially started out moving a camera in and out so as to get more detail around a specific zone axis, and then used cross correlation to really quantitate that detail, the differences between different zone axes, or zone axes from different patterns. He took that a step further and applied different regions of interest within a pattern, and then did a cross correlation between different pairs of regions of interest to find the displacement of the zone axes or the bands essentially during when they're strained. And from that you can calculate a displacement vector. And so really this, to my mind, is advanced pattern analysis, at least more so than what we typically do with standard indexing. So with HREBSD, there have been ideas to use simulated patterns. The initial papers used kinematic patterns, kinematically simulated patterns, and that got us a certain step forward. But now with dynamic simulated patterns, it looks the future looks much more promising to incorporate that in, which would give us more information about absolute strain and some other features that we can find in the patterns themselves. And as an advance on the cross-correlation work, some work has been done using full field cross-correlation using the DIC framework, using the ideas that are used for speckling, but just within the patterns themselves. Also, we've seen recently more work done on using the bands in terms of the bandwidth. We used that back at some of our very first experiments to try to help us in indexing, but now it's being used to look at things like strain, to look at an ab initio determination of the unit cell. And so I can anticipate that being in greater use, and probably coupled also with some of the cross-correlation ideas. Detectors have come a long way since those early results. I mentioned 4.3 patterns per second. Part of the reason we're faster is the algorithms, but also it's because of the hardware. So let me show some examples. Now, the very first EBSD patterns were collected on photographic plates and then film. This is an example of Venables and Harland, which was the first introduction of EBSD into the SEM. And you can see we're detecting electrons directly on Polaroids. The next step was an analog TV camera, with David Deemley introduced to help with online indexing. And then we saw SIT cameras. This was my first exposure, was using a SIT camera. And from there, we went to CCD cameras. Here's an example that Joe Michael showed with a YAG screen. And then we went to digital CCD cameras, which took us quite a ways. But recently, we've started to use CMOS cameras. This is just the one we introduced. There's others out there, of course. And this gave us a lot of speed. And that has been speed has been the focus of detector developments really for most of the time. And with the CMOS detector, we can get a lot more pixels a lot faster. It doesn't have the on hardware binning or on sensor binning that we had with the CCD, but CCD sensors are disappearing as CMOS has taken over the market due to its effectiveness and, frankly, our phone cameras. But that gets us so far. We can do really fast scanning. You can see here 1 million point scan in less than 4 minutes, which is just remarkable compared to where we started. But it's been a focus on speed. And the question is can we improve the quality of the patterns, take a different approach? And we know there's distortions in the patterns due to the lenses or due to fiber optics or whatever we're using in our whole detector system. It's also, we get effects from the scintillators, whether it be phosphors or YAG crystals or some other detectors. So now we're looking at direct electron detection. It is based on a CMOS, but that's behind the scenes. We really are using using a sensor to actually count the electrons at each pixel. So here's an example on a seashell. You can see it right. The results from our new clarity detector. Very beautiful results at 12 kV, 800 picoamps, not something we could do with the CCD detector. And you can see the kind of detail we can get in that region that we had a tough time indexing with our standard CCD detector. And in this, we are really counting electrons instead of really just picking up intensities. And you can see the detail it gives us compared to our CCD detectors. just a lot sharper detail, a lot more of the more subtle features in the patterns. And you can see this is compared to dynamic simulation. We get really sharp results rivaling that we see in the simulation. If you zoom in, you can see that detail that we get. And it's interesting because we've noticed that we see some things in the direct electron detected images versus those we see in the simulated, and some things we don't see. So it's kind of interesting. I anticipate this telling us something about the physics of pattern formation and defects and things like that. Could be quite interesting going forward. I also hope that with these kind of cameras, we can improve our HREBSD work, improve our indexing in general, but we can also start to look at things like non-centrosymmetry, symmetric crystals, which we really can't look at all, without including the symmetry in the crystals we look at today with standard EBSD systems. So I think the direct electron is going to be an exciting future for EBSD. We can start to look at beam-sensitive materials in more detail, like I showed an example of. It should help with HREBSD because we've taken out the lens and the phosphor screen. We expect it to help us understand the physics of pattern formation better, especially as we incorporate potentially energy filtering into that, and maybe even get us to different geometries. I do expect 3D to continue to improve as it has today. We've seen great advancements with robotics. An example at right from Dave Rohnhorst. We see the improvements with laser milling at the tri-beam. Introduction of plasma fibs certainly has helped too. I also anticipate maybe someday we'll have in situ broad beam ion milling. That could be on the horizon as well. I've seen some examples of that in the literature. Obviously, the improvements we make on detectors, compressed sensing, or the sparse data collection could help also with improving 3D results. And another brief one, TKD. I could anticipate improvements there with either improved Hough transform, but more likely to see improvements using dictionary indexing, whether it be the straight dictionary indexing or spherical. And also briefly, sample preparation. I think the biggest improvement we have seen is with broad beam ion polishing as it's become more EBSD focused, but there's still difficult materials out there that we need to overcome and make improvements on, and so there's certainly room for improvement there as well. Other challenges that I see that we need to overcome is with our SEMs. As the microscopes, the smaller spot size we can get with the most current we can get obviously will always help EBSD. Stability of the systems, geometry, whether it be for EBSD and TKD in the same microscope or incorporating other correlative microscopy. Part of that would be just improvements in the imaging fidelity at tilts. Big data with these faster cameras that we have, it's getting more cumbersome to carry all that data around, which I briefly mentioned, so we need smarter analyses. But we also need to take greater advantage of the improvements in the computers. Both for the users who need to be a little bit more aware of the demands that we're placing on the computers, and you have to make a greater commitment to computers and can't just use a simple off-the-shelf laptop necessarily to do the kind of analyses that we all want to do. As developers, we need to take a greater advantage of the computing hardware improvements, whether that be using GPUs for calculations, more multi-threading, better management of memory and the data storage. The end goal obviously is not to publish technique development papers, but really to create real progress in the use of EBSD to improve materials performance and as well as the forming processes. I'm sure there's other things than what I've thought of here, and I'm sure there's exciting things in the future. Like I said, EBSD has certainly not plateaued. There's certainly room for improvement and exciting for the future of EBSD and technical development. And with that, I'll close, and thanks for your attention.